Welcome to this presentation, Visual Trace Diagnostics with STLINK-V3, Percepio Tracealyzer and DevAlert. My name is Johan Kraft. I'm the CEO at Percepio in Sweden. I founded Percepio in 2009. I'm a PhD in computer science and the original developer of Percepio Tracealyzer, our original product. I will start by explaining what we mean by Visual Trace Diagnostics that Tracealyzer provides, and what it's good for, and how it benefits development projects. Then I will also spend a bit of time on IoT device monitoring with Percepio DevAlert. And then there will be a demonstration of how to use Tracealyzer with STM32 and STLINK-V3. First, about the general capabilities of this tool with respect to software visualization and the capabilities there. And then how to set it up with STM32 Cube IDE. And then how to configure streaming mode using the STLINK-V3. Tracealyzer provides visual trace diagnostics for developers of RTOS and Linux-based embedded systems. This allows for recording and visualizing the software at runtime. This supports any STM32 processor, STM32 Cube IDE, and STLINK-V3. We support RTOSes like FreeRTOS and Azure RTOS or ThreadX, including live streaming in real time. For multitasking embedded software, the source code does not give the full picture of the runtime system, which can be seen a bit like a black box or the dark side of the code, if you will. Visual Trace Diagnostics gives you a detailed visual timeline of the runtime system and a large set of visual overviews, metrics, and statistics. This makes it far easier to debug system-level issues, problems that are detected when running the full system, which otherwise can be quite difficult and time-consuming to resolve. Moreover, you can also find software design flaws as early as possible, and thereby improve reliability, performance, and reduce the risk of future problems. Finally, it makes it easy to measure timing and performance metrics for verification of real-time requirements and for tracking and optimizing software performance throughout the development. It allows for continuous live streaming of trace data from the target system to host, so you can monitor the system over long periods of time. You can even see live animated views of the data. Let me show you what live streaming looks like. We just click Start Recording and Tracealyzer begins to receive, process and visualize the trace data in real time. This application is a PID motor controller, and we can see the control signals in the bottom right view: target position, actual position, and motor torque. These are variables in the code that we are logging with Tracealyzer. On the left, you see the trace view showing the execution of RTOS tasks and interrupts. Once we have recorded the software behavior of interest, we stop the recording and thereby enable all views and features in Tracealyzer for more detailed analysis. Tracealyzer supports embedded Linux and the following list of real-time operating systems. Streaming is supported for most of these platforms. In other cases, the recorded data is stored in a target-side RAM buffer, what we call snapshot mode. Software tracing is nothing new, but raw trace data is difficult to use in practice. Viewing this in a text editor isn't very helpful. You get large amounts of low-level events, where most are irrelevant repetitions of the same patterns. You can't see the forest for all the trees. To really benefit from software trace data in everyday development, the solution needs two more components. The data needs to be processed into a meaningful model describing how each event affects the system state. The data needs to be visualized to allow quick intuitive comprehension and actionable insights, even for large datasets. The human brain is visual and excellent at pattern recognition, especially at spotting anomalies in repeating patterns. We can leverage that by showing visual overviews from different perspectives, such as graphs over CPU load or task response times. Finally, by connecting the views, we allow for a top-down workflow that is ideal for system-level analysis. Spot anomalies in high-level overviews and drill down to inspect the details. We call this Visual Trace Diagnostics. This is useful for debugging purposes whenever you need a timeline for your software. This is often the case when debugging a full multitasking system, and especially important when the location of the bug isn't obvious from the symptoms. When the issue is difficult to repeat, perhaps it only occurs once in a while for no apparent reason, or when interactive source code debugging can't be used, perhaps since the system can't be halted for debugging, or that you physically can't connect a debug probe. While many still use printf debugging in such cases, Visual Trace Diagnostics is a superior alternative. The logging is much less intrusive, about 100 times faster than a printf over a serial port, which allows for logging much more information, also from the RTOS kernel. And the data is easier to analyze, even for large datasets, thanks to the powerful visualization. This means less debugging time and more time available for customer value creation. And with better ability to solve complicated bugs, you reduce the risk of project delays or having to work 100 hours per week to make the deadline. Finally, better insight during debugging means less guesswork involved, which is likely to improve software quality as the bugs are fixed properly. Another important use of Visual Trace Diagnostics is to find software design flaws as early as possible. There are best practices in RTOS software design, and these are important to follow. By design flaws, we mean deviations from these best practices. They are not necessarily functional errors, but they may reduce performance and responsiveness, increase the risk of future bugs, and make the system testing less effective. Design flaws are important to find early, otherwise you might find yourself in debugging hell when the application grows, which may require a major redesign of the software. This is much more difficult in later stages of the project. The earlier you can find software design flaws, the fewer changes are required to fix them. Last but not least, Visual Trace Diagnostics can be used to measure software timing and resource usage. This way, you can verify real-time requirements and keep track of the software performance and resource usage throughout the development project. Tracealizer provides timing metrics on task instance level, where you get a data point for each execution, each job of a task, such as task execution times, task response time, periodicity, etc. You can also define custom intervals based on user events that you add anywhere in your code, and then see the time between these events. This way, you can ensure compliance with real-time requirements of your application, keep track of product performance, and find ways of improving it for a more responsive and capable product, improving customer satisfaction and sales. This can also avoid project delays by enabling early detection of any performance issues. DevAlert provides real-world feedback, allowing for rapid, continuous improvement of the device software. It's a cloud-based solution for IoT device monitoring, focusing on the actual software on the devices. This makes it easy for device developers to report any error, warning, or other event of interest during runtime from the devices back to the developer team. This can be used both during testing and in deployed customer operation. By having this in deployment, you will know about real-world issues within seconds after the very first occurrence, instead of having to wait for weeks or even months before some users bothers to report the problem. By having DevAlert enabled during testing, you ensure that issues that are encountered by testers are captured systematically and in full detail and are provided to the developers immediately. So this is really a cloud-connected flight recorder in your embedded software. When an issue has been reported, your development team can then analyze the issue with Visual Trace Diagnostics to understand the problem and the specific circumstances where it happened, which speeds up resolution tremendously. This awareness of real-world issues and the provided diagnostics means that you can take full advantage of over-the-air updates to achieve rapid continuous improvement. This is likely to improve product sales, as you can catch and fix those remaining bugs quickly after the very first occurrence, before most of the users even have noticed any problem. Higher average quality means higher customer satisfaction, meaning better product reviews and more loyal customers. Improved reliability reduces not only liability risks, but also the costs for customer support, returns, and debugging of customer issues. The provided diagnostics makes it far easier for developers to reproduce customer issues, since they get information directly from the device automatically and don't have to rely on the users to describe the circumstances. Feedback on real-world product performance allows for improving key performance metrics and the overall user experience, so you can make a great product that beats the competition. This is the DevAlert dashboard that provides an easy overview over recent issues. By issue, we mean all alerts that are of the same alert type and have the same symptoms. For instance, the alert type might be malloc failed, meaning that the system has run out of heap memory, while the symptom could identify the location in the code where it happened or how much memory you tried to allocate. The developer can define their own alert types and symptoms as needed. Alerts also include software traces, and these are directly accessible from the dashboard. Just click the links and the trace file is downloaded. The data flow starts in the device source code, where developers add alerts at strategic locations, such as existing error handling code and hard fault exception handlers. When an alert is uploaded, a snapshot of this trace buffer is also included. Since this is a ring buffer, you automatically get the most recent events that preceded the alert, and that most likely can explain the problem. This data is then uploaded to the normal cloud account of the IoT device, just like any other application data, and with the same level of security. Once the alert data reaches the developer account, the upper part, that is the alert signature, is then forwarded to the DevAlert cloud service. This is a fully managed cloud service provided by Percepio, but the trace data is not forwarded to the DevAlert cloud service. It remains on the device developer side at all times. When the DevAlert cloud service gets the alert signature, it is compared with previous alerts from the entire device fleet and classified into unique issues. Notifications are sent to the device developers, but only when a new issue is detected, not for each and every alert. This way we avoid flooding the developer's inbox if the same issue would occur in many devices. Once notified, the developer then opens the DevAlert dashboard to overview the recently reported issues. Finally, the developers can use Tracealizer to analyze the provided traces. You will learn more about Tracealizer soon in the live demo. So, how are the alerts generated in the code? Here is an example where a FreeRTOS error handler has been extended with an alert. We begin by storing a user event in the trace buffer. This is a convenient way to highlight the alert in the trace and provide greater means for additional diagnostics, as you can store formatted strings and values much like a printf call. Then we stop the trace recorder momentarily, since we don't want any changes in the trace buffer while reading it. Next, we compose the actual alert, the data package, by setting the alert type and provide additional diagnostic information as symptoms. You may add your own alert types and symptoms as needed. Finally, we upload the alert and resume the tracing in case another problem would occur. Okay, now I'm going to show you a demo of Percepio Tracealyzer, our tool for Visual Trace Diagnostics. I think it's important to show you this for real, so to say, to give you a better picture of the possibilities with Visual Trace Diagnostics. Now I'm loading a pre-recorded trace from a FreeRTOS system, but Tracealizer looks and works the same for all supported platforms. We also support ThreadX, Linux, VxWorks, and a few others. Let's begin with the event log, which is the most detailed view in Tracealizer. It shows the recorded data as is, event by event. I like to think this illustrates the need for visualization. Tracing generates a lot of data, several thousand events per second. Software traces are mostly repetitions of the same patterns, but it's often the deviations, the anomalies, that you're interested in. But with this amount of data, a plain listing is not very useful as a starting point, unless you know exactly what to search for. But that's typically not the case when you're investigating a problem found at system level. But once you know what to search for, you can do it here. Just type in a few characters like this and select apply or hit return, and then only the matching events are then displayed. This particular event is what we call a user event, produced by explicit application logging. This way we can see the values of a variable or when a certain point is reached in the code. Unlike regular printf calls, which can be really slow, milliseconds, user events are generated by calling the trace recorder library, and the overhead is then measured in microseconds. This approach also integrates both kernel event tracing and application logging in the same data stream. We can double-click on this event to highlight it in the trace view. This way you see the context of the event, what was going on in the software at this point. Currently we only see the scheduling, but much more information is available. Let's begin by zooming in a bit. The trace view is vertical by default. Time goes downwards. This makes it natural to scroll with the mouse wheel, like in the source code, and it also allows for showing event labels in the trace. Currently they are disabled in the filter, but we can enable them like this. The leftmost part of the trace view is the scheduling field. The columns are what we call actors, meaning execution contexts, tasks or interrupts. They're colored and sorted by scheduling priority. The solid rectangles are what we call fragments, the time between context switches, so uninterrupted execution. This blue outline, when you select a fragment here, is what we call an instance. It represents a full job or execution of an actor task. This is typically a single iteration in the main loop of a task, and it can be multiple fragments if the task has been preempted. Here you can see an example of an instance with multiple fragments. This green task HMI has been preempted several times by higher priority tasks, and thereby you get this effect. We can see more information about the selected actor in the upper right corner, selection details. For instance, execution time, response time, and such metrics. But let's go back to the previous location. When zoomed in like this, the trace view is quite similar to the event log, and you wouldn't want to scroll through a large trace at this level. But unlike the event log, the trace view allows for a better overview since you can zoom out and adjust the filter. This kind of trace visualization works also when zooming out over long durations. Now the view is a few seconds, 25 seconds, minutes. We're now looking at 3 minutes of trace data, 700,000 events, but you can still see the distinct modes of operation in the system, and by changing the filter, we can still see individual events of importance, even in this very zoomed out view. We can then zoom in on interesting parts like this. Okay, so now you have seen some of the more detailed views in Tracealyzer, the trace view and the event log. But before you can begin a detailed analysis at this level, you need to find the relevant locations in the trace, but often you don't know exactly what to search for. For this purpose you need a top-down workflow, where you can spot anomalies in visual overviews and reports, and then easily drill down into the details. Next, we'll take a look at some of the overviews that Tracealyzer provides. One example is the CPU load graph. This shows how the processor time is distributed over the timeline. Here we have a horizontal timeline, so time goes right. We can zoom this view independently of the trace view to get more overview. And if we click on any of these bars, it shows us what happened there. So you can use this to profile your system, see where your CPU cycles are going, but it also shows you the dynamic profile where the activity is that you can use to navigate in the trace. Next, let's take a look at the user event signal plot. This shows a plot of the data we have logged as user events. Currently we see just the target pos variable, but let's add the others. There are many ways to adjust the display. Here I'm changing the line style from straight lines to steps. That looks better for target pos. And just like with the CPU load graph, if you double click on a data point, you see the label in the trace view like that. This application is a PID motor control loop. So if you see an anomaly like a large overshoot, you can just click on that and see where in the trace that occurs and the reason for that. This is really powerful in combination with live trace streaming, where you see the data in real time. In streaming mode, the data is transferred continuously from the target system to Tracealyzer and processed on the fly. And this way you get these live animated views. This gives you an immediate feedback on what the system is doing. If you're pushing a button on the device, you'll see directly the impact on CPU load and user event signal plot, etc. You can pause an individual view like this and zoom in and out, etc. while recording, so you don't have to stop the recording session to inspect some interesting detail. Not all views are enabled in live mode though, so we stop the recording when we're finished and then enable all the capabilities of Tracealizer. Note this checkbox in the live stream window. This allows you to record continuously for hours and hours, only storing the trace to disk without the live visualization. This way you can record really long traces if necessary, many gigabytes. To open a long trace like that, you use the trace preview feature found in the file menu. This allows you to select an interesting part of a trace and load that separately. The preview is based on an index file that is created while recording the data. This way we can load a short section of a much larger trace in just a few seconds, like this. Okay, let's go back to the previous trace. I have a few more things to show you. Let's take a look at the communication flow graph. This is a dependency graph that shows the runtime interactions between the different tasks and interrupts in the system, who is talking to who in runtime basically. This is generated from the trace data. The rectangles are execution contexts, actors like tasks or interrupts, and the ellipses are objects like queues, semaphores, mutexes. The arrows are the API calls that form dependencies between tasks or interrupts and these objects, like the HMI task is using this particular queue, for instance. You can click on the nodes in the graph to see a list of all operations on these objects, and then click in that list to find them in the trace. In the case of a queue, for instance, we can see a visualization of the buffering in the queue and match the send with the corresponding receive events, and thereby follow the data flow through the trace. This way, if a task receives bad data from another task or an interrupt, you can backtrack and find the location where the data was generated. Okay, so to set up Tracealyzer with STM32Cube IDE and ST-Link, we start with an empty project for an STM32F4 board. Tracealyzer works with any STM32 device though, so the exact one doesn't really matter for this demonstration. I just need to find a project, this one, for this board. And we have some FreeRTOS projects here. Let's take this one with queues. And we create the basic Hello World project, basically. Okay, let's build the project to see that it works. Looks good so far. Let's start to add the Tracealizer recorder files as well. We create a couple of folders for this code to make it tidy. We called the top folder tracealizer, and then we create a couple of subfolders for different types of files. src for source, inc for include, and cfg for configuration files. So we'll copy these 3 C files into the source directory, and we select copy rather than link. And then the include files. And then we have some other include files that contain configuration options. In the config directory we include them as well. Note that the recorder source code, this trace recorder code, is found in the tracealizer installation directory. Now we also need to open freertosconfig.h to make a small change there. It's a bit difficult to find, but it's in the FreeRTOS header somewhere. No. Yeah, here. This one. So here in freertosconfig, we need to make sure that the trace option, config use trace facility, is set to 1. Yeah, here it is. Yes, this one, good. And in the end, we need to add an include of the main header file of the trace recorder, include trc recorder.h. Like that. This basically connects the FreeRTOS kernel to our trace recorder library. And then we need to make sure that the include path is updated to find the header files of the recorder. So we include the folders we created for include and config. Like that. Okay. And we need to also take a look in the main configuration file of the trace recorder library. First we comment out this line, which is just a reminder, and include the processor header file. This is required on ARM devices to access the SIMSYS library that is used by the recorder. Then we set what hardware port to use, and this is a Cortex-M device, so we use that. And then we update the FreeRTOS version so that the instrumentation is correct. Otherwise you might get build errors actually. Okay, so now it's building in the default mode, snapshot mode. In snapshot mode, the data is recorded to a ring buffer in RAM. And to enable it, we also need to add a call in main, or before any RTOS calls are made actually. Typically here, vtrace enable. And the parameter here, trc start, means that the tracing should start right away. Okay, so now we are building it, and now it should work in snapshot mode and provide a trace in a RAM buffer that we can read with the Percepio plugin that I will show soon. Okay, so let's open the debug configuration and just check that it looks okay. Yeah. Let's enable serial wire viewer. We'll need that for streaming later when we enable that, and we need to set the clock frequency correct, so it's 168 megahertz in this case, and nothing else there. Okay, good. So now we should be able to test this in snapshot mode. So we start it up and run a debug session. We can actually verify that the clock frequency is correct, we'll set a breakpoint after the system clock config has been called, and we inspect the variable system core clock, which is from Synopsys. Yeah, it's 168 megahertz, correct. Okay, now we can run it, and we let it run for a while and then break and see where we ended up. Okay, we are still within start scheduler in FreeRTOS. This doesn't look right. There is something wrong here. Let's see if we got a trace and if we can see something there. But first we need to update the settings in the under preferences in the Percepio plugin. We have to specify the path to the tracealizer exe and set FreeRTOS as RTOS. Okay, now we should be able to read a snapshot trace. Here is tracealizer opening the data, and we see actually here there's a malloc that returned null. So it seems that the system ran out of heap memory during the startup. Okay, the FreeRTOS heap is configured in FreeRTOS config, so let's take a look at that. Up here, okay, it's only 3 kilobytes, that's way too small. This has nothing to do with tracealizer, this is just for task stacks and stuff. Okay, so we set it to 10 kilobytes and recompile. Okay, let's try again. Okay, let's run. Let's remove that breakpoint. Okay. And pause. Yes. And then we have now executed the system for a while, and it seems to work better now. We are in the idle task of FreeRTOS. We save the snapshot buffer, and it's then open automatically in Tracealizer. So here we can see a visual timeline of this basic application. We zoom in here on this point where we have a couple of tasks running. We can see some events, and in the communication flow graph we see an overview of the application. So it's basically just 2 tasks here with a queue where messages are sent and received. We can click on the messages here to on these operations to see where in the trace they occur. There is a lot to talk about regarding Tracealizer and all the features, but let's try streaming mode as well. So to enable streaming mode, we just need to change this option and set it to streaming. And then we build. Oh, we got an error. Okay. It can't find trc streaming port.h. I forgot to include that. This file, trc streaming port.h, it specifies how the data is outputted. And we have a couple of options here. This is for USB CDC. We're not going to use that, but ARM ITM for when using ST-Link. So I'll copy this code to the source folder, and also to this include file to the configuration folder. And let's have a look here. I believe there is some setting here. Yeah, the ITM port needs to be selected. The ITM debug interface has 32 different ports you can select. All go out to the SWO port, but this is a logical channel. We have selected 1. That's fine. We just have to remember that when we set up Tracealizer. Okay, so now it's compiled in streaming mode. Let's start a debug session. Now we need to check the SWV settings. If we go to one of the SWV views and select the options, we need to enable this ITM channel, channel 1. And the rest was fine. Let's enable tracing here in the IDE and see if we get some data. Yes, we do. We get data. Let's see if we can get this into Tracealyzer then. Now the board is free running, so the ST-Link is free. That's important because Tracealyzer and other tools can't access the ST-Link at the same time. So to set up Tracealyzer for ITM streaming, we go into File Settings and select PSF Streaming Settings. It should be set to ST-Link ITM. The prescaler 16 is a good value. It can be a bit smaller, maybe 14 to improve the throughput, but 16 is good. And here we go. Now we see a live streaming view in Tracealyzer of this FreeRTOS application. And then we stop the tracing and get access to all the different views in Tracealyzer. We have more than 30 different views. That makes it easier to debug at system level, analyze the software design and improve it so your application gets better performance and runs more efficiently. In short, Tracealyzer is the leading solution for visual trace diagnostics and provides several important benefits. Easier debugging of system level issues, finding software design flaws, and verification of timing and performance. This saves time and money by less debugging time, reduces the risk of project delays, improves product reliability and performance, and frees up developer time for important customer value creation. To learn more about Percepio Tracealyzer and Percepio DevAlert, visit our website percepio.com. Thank you.